PolkaVM is a RISC-V based general purpose virtual machine. RISC-V based means it's a register machine, and its instruction set architecture looks like a lot like RISC-V. We made minor modifications to it, mainly to make it more on-chain friendly, and it supports the RISC-V embedded instruction set architecture. And so what you do is you just compile your programs to the CPU, and then our linker translates it into a PVM blob that then is executable by pallet revive. PolkaVM provides very efficient compilation because RISC-V is very close to x86 bytecodes. So all those hard annoying problems, compilation problems that we have with WebAssembly, they actually just don't exist. So we can compile those programs much faster. And it also means that we can let LLVM or whatever good compiler framework spend a lot of time off-chain producing like very, very optimized blobs. So this means we have like very efficient compilation, and the contracts we are execute are actually like very optimized and fast. And yeah, PolkaVM also has gas metering with a gas model suitable for contracts, which not all WebAssembly implementations have. So as it is a standard, if you have portable code, for example, JVM or also Node like the V8 engine does this, you can actually either interpret or JIT compile the PVM blob. Interpreting it means you can start execution instantly like the EVM does. So interpretation is obviously also much slower, but it might not matter because, as I said before, if your contract does not do a lot of work, like interpreting it will always be faster than compilation. But if you also can compile your contracts, yes, you pay a fixed upfront overhead, but after compilation, your code executes much faster. It executes in near native code speed, and with this I mean actually near native speed, not as we'll see in some benchmarks. And contracts on Polkadot Hub will support both. We just start with the interpreter, and the JIT compiler will follow later. So what this translates is more or less whether to use the interpreter or the compiler is kind of an optimization problem. So if you don't have a lot of iterations, as you see on the bottom left, you might want to use the interpreter because that's faster. But the more iterations your code does, so if you imagine something like calculating Fibonacci numbers or calculating a hash, then like the more iterations you have, eventually will reach a tipping point where it might be worth to use the compiler. And here are some benchmarks. So what this does is it executes a NES emulator, and so we can compile this. It's called Pinky, and we can compile this Pinky NES emulator to various virtual machines. So we have the PolkaVM recompiler, the PolkaVM interpreter, Solana, RBPF, and WASMI. WASMI is like what the old contracts, the WebAssembly-based contracts palette uses. And we also have WASM time here, which is what parachain validation function uses. It's like the state-of-the-art WebAssembly compiler, the state-of-the-art WebAssembly implementation. And what we see here is like just what I said before. The recompiler has a bit of compilation time, but it's execution times are like very, very fast. So WebAssembly wasm time is considered to be like top-notch standard, like the best of the best compilers for WebAssembly. And PolkaVM, and this is not even like very well optimized, it just executes this interpreter faster than the fastest WebAssembly compiler. And then what we also see is the interpreter, while it executes a lot slower, it has zero compilation time overhead. So there's nothing missing here. It just doesn't show up because it instantly starts executing contract code, which is again very beneficial if you just, for example, do a token swap which executes dozens of instruction or hundreds of instruction, then you probably want this. And then we see like existing solutions, Solana and WebAssembly contracts. So they don't really excel in leader metrics, right? So their compilation time is like quite high, but also their execution time isn't very something to brag about. And with PolkaVM, we can basically have best of both worlds. So what this does, this unlocks new use cases that are so far not really possible. But so you can just, instead of a parachain, write your code as a contract once the JIT compiler is available, because it will execute around the same time as your native WebAssembly code. If startup overhead is feasible for you, you can also have interpreter contracts for other languages. So we might as well see Python or JavaScript, or like, Move or Solana contracts on Polkadot Hub. And if you, let's say you want to verify a Stark proof, and then what you do on Ethereum, you always have those recursive snarks, because there's very few curves, and so very few verifiers that actually work on chain. And then you always have to
Hello, everyone, and especially the fellow hackers. Here we are to basically get started with the first ever workshops in the series that we're going to have. So earlier we were planning to have just one workshop and one AMA to solve all the doubts, especially with live coding. And now we actually got more interest from our judges and mentors. So we'll be having not just one, not just two, but actually four mini workshops during this whole eliminator round period. So today the aim will be pretty simple. How existing Solidity developer, or even like if you are a very beginner level developer, this is where you can get started. So today we'll be covering what are the very minor changes that you need to do in order to make your contract compatible. Like most of the contracts might be compatible with PolkaVM right away, but some contracts might need slight changes. So we'll go through all those changes today with an example, a demo, followed by all the questions from our fellow hackers. So let's get started with our first session, which will be taken care by Raj. Before we start that session, I will quickly give introductions of our today's host. So I will be moderating the panel, but Raj and Abhiraj, who are taking care of this whole session from the technical point of view, are existing PBA grads, and they are actively working in the Polkadot ecosystem. So Abhiraj is currently working with Muntak Labs. He also recently got funded from Open Source Bounty and currently have a proposal in Fast Grant Bounty as well. So pretty active contributor, I must say. And same goes for Raj as well. So Raj and Abhiraj actually are from the same batch of PBA from Singapore edition, and from there they actually parted their ways, pursued their own vision, and after a while, actually, we when we came up with the idea for workshop series, at that time we collaborated again. So Raj is a developer who had like extensive Web2 background as well. Then he started contributing to one of the substrate ecosystem chain Edgeware, and then he like when distributor subdao was formed, he became like one of the co-founder of distributor subdao. So he's been like crucial part of all the initiatives that has been taken by the distributor subdao, whether they are technical, non-technical, curation, education, development. So all those he was actively involved. So that's like a short introduction about Raj and Abhiraj. So I will now request Raj to take it over.
Get an overview about like what's Polkadot, what's AssetHub, what are like system chains,
Raj, sorry
what's
to interrupt. Actually, you was on mute. So I just unmuted you. Can you
hello,
please start from the beginning?
hello,
Yeah,
can you
you are
hear?
audible. You are audible.
So yeah, we are gonna first, the flow would be like this. We are gonna get an overview of like what is Polkadot, like what are system chains, then what actually is Plaza, then like EVM contracts, WASM contracts, Risk 5 and PolkaVM, and then we'll get to deploy one of the contracts to get a feel of how the developer experiences while deploying those contracts. So I'll kind of start sharing my slides now. So give me a minute, just a minute, just a minute. Can you see my screen? Can anyone confirm?
Yes, it is visible.
It's not the correct slide though, right? Just a minute. Yeah, you can see it, right?
Mm-hmm, mm-hmm.
So what we are talking about is like contracts on Polkadot basically. So this hackathon is about deploying Solidity contracts on Polkadot. So and how do we actually achieve it? So this is like our agenda where we will discuss about the basic architecture of Polkadot, our overview of the new Risk Firebase stack, and a demo at the end. So what is Polkadot, right? Polkadot is like many things, right? When you talk about Polkadot, you can think of it like the Polkadot ecosystem. You can think of it like the Polkadot relay chain, which secures all the other para chain, or you can like think about the Polkadot network in general, correct? Uh, so we are going to focus on parachains, like what are parachains in the context, like in the context of Polkadot, correct? So parachains are kind of roll-ups. Uh, it's not completely correct, but one of the key people in the Polkadot ecosystem, he once said in this tweet that parachains are just roll-ups that are done in a right way. They kind of settle on the same base chain. They speak the same language for interoperability, which is what we call XCM. They use the same SDK and save massively on the costs. It comes with governance out of the all. They can scale thousands of TPS, and sequencer decentralization comes out of the box. You can even run EVM out of the box if you want, correct? And the parachain collator produces something called as validity proofs of the parachain blocks, which are then sent to the relay chain validators, and relay chain validators sort of re-execute and prove the correctness of this parachain block. So in the case of this hackathon, we are going to be deploying contracts on one of the parachains, but which is kind of called a system chain. So let's speak about something called as dApp chains. So the purpose of the relay chain should be to only verify the parachains and provide security. There is, like, when we speak about deploying contracts on Ethereum, right? We are either speaking about the mainnet, or we are either speaking about deploying contracts on any of the L2s, right? But there is no like contracts on Polkadot, correct? So instead, in Polkadot, like, everything is a parachain, right? If you think about something like a DEX, it would be a specialized parachain uh, in the Polkadot ecosystem. You think about NFTs. There would be a specific parachain specialized in that use case, correct? So these aren't called dApps, but they are kind of called dApp chains. Basically, those that are not a contract but a specialized chain in general. And this is the case that is with Polkadot. So we are gonna speak about these four things: what is Polkadot Hub, what is Palette Revive, and the Solidity compiler. And before we move on to that, before we move on to knowing what Polkadot Hub is, let's talk about system parachains. Can anyone, you can see my screen, right, guys? Hello. You can see my screen, right? Yeah. So let's talk about system chain. So there is something called as the minimal relay chain vision, where the thing is that the relay chain, as I mentioned, it should verify the parachain execution, like it should secure those parachains and guarantee the parachain execution, and they should also be able to communicate with each other, right? They should relay messages between each other. And the core functionality, like like in the case of like if you want to issue an asset, those should be moved on to moved on to the parachains, like, which are called the system chains, be it like balance transfer. Like, uh, bridging within the ecosystem is fine, but if, like, what if you want to bridge beyond the ecosystem, right? Or if you speak about governance or dot staking, those should be moved from the central relay chain to one of the parachains, and that system parachain for us is like AssetHub. Okay. And these system parachains are governed by the technical fellowship. And if you think about the kind of token, right? Like, a parachain can have its own token if needed, or it can have the same token as the relay chain. It depends on the parachain. But in the case of system chain, that we are using dot, you just have to teleport your dots across to this asset hub chain. So basically, system, you can call system chains as being just a parachain. uh, Next. And as we spoke, right, about the minimal relay chain vision, it's just the same thing. Take balances, take staking, take governance on its, and many other things among it to its own chain, which is own chain, own system chain. And in our case, in Polkadot, it's like it's being migrated to the asset hub system chain, and thus we are kind of implementing this minimal relay chain vision. So this is the same thing I was talking about, of moving those core functionalities to the asset hub chain. That's the minimal relay chain vision. So now we want to support smart contracts on Polkadot, and when I say smart contracts, I'm not speaking about WASM contracts. So we want to have the minimal relay chain vision, plus we want to be able to deploy contracts on Polkadot. And when I say Polkadot, I mean the asset hub, correct? So when the minimal relay chain vision and this ability to deploy contracts comes together, this is what we called as a plaza upgrade for asset hub. And this was something this was something spoken about in one of the blog posts by co-founder of Polkadot, Rob Habermeyer. That is a good article you should have read about. So basically, we are moving from asset hub to Polkadot, right? We are moving the core functionalities to the from the relay chain to the asset hub. We are adding contracts to the asset hub. So conceptually, this kind of turns the asset hub into something called as a Polkadot hub. So why do we call it Polkadot hub? Why not call it Polkadot? Because as I said in the beginning of the slides, right, Polkadot is like many things, right? Polkadot can be a DAO, right? Polkadot can be the relay chain or the network of chains, correct? So just to stop that confusion, like we are calling it Polkadot hub, which is the system chain, which is one of the system chains of Polkadot. So one thing we must keep in mind is that uh, just deploying on just having contracts is not kind of exciting, right? We have all these pallets, like pallets that make up our runtime, right? And we want to kind of make use of these pallets. So what we are going to do is we will expose the API of those pallets as a pre-compiled contracts. Like imagine a pre-compile at a specific address, which you can call and interact with the Polkadot governance. Imagine how cool would be that. So we want those pre-compiles to kind of understand the Solidity ABI, and we can have a Solidity interface, and behind that pre-compile address, that would be this palette. So think about, like, you know staking, governance, being able to tap into all these exciting core protocol features that are chain exposes to us. So if I want to talk about, like, if we have to summarize everything, so asset hub, currently this asset hub system chain is for, like, asset issuance and, like, basically managing assets, right? The plaza upgrade, asset hub turns into something called as a Polkadot hub. Contracts on Polkadot, or we say Polkadot hub, this just means contracts on asset hub. This is basically, like, centralizing all the network functionality. By that I mean this, taking the governance, everything into a single place, which adds a layer of this permissionlessness and synchronous programmability, and it kind of looks Polkadot like any other L1 blockchain. So moving on to palette revive. So we want to deploy RISC-V based contracts, and we want to provide an environment for contracts and contract developers that looks a lot like EVM environment, correct? And it doesn't kind of matter on what is executing. It doesn't matter what is executing the contracts under the hood, or what bytecode it is, as long as we provide the correct APIs, right? We want is EVM like runtime API, and we need a contract storage as well, and sandboxing, because contracts are just untrusted code, right? You just don't want it destroying the host, right? So in our case, like PolkaVM in our case is like a RISC-V based virtual machine which can support any language. And what the role of palette revive is to make sure to invoke the PolkaVM to execute our contracts, okay, and have a general compatibility layer like RPC interface, transaction receipt, and be ability to map these Ethereum address to our substrate style accounts. Because like if any one of you might have went to Polkadot.js apps and looked at palette revive, if you had a chance, you will. Uh, it's also mentioned in the docs, right? You can map your substrate address, This is basically one of the things. So like, what's wrong with wasm contracts, right? uh, like, we were using wasm contracts, correct? Even the runtime has something, parachains kind of use this wasm. So wasm is like often praised as this faster alternative to EVM. There is a whole lot of adoption, and a lot of blockchains have this WebAssembly contracts. But wasm is not like like an actually like an instruction set. It's kind of more like a programming language. And when I say programming language, right, it means when I say programming language, it means a whole lot of loops. uh, and wasm is not like a register machine, it's a stack machine, right? So it's a stack machine executing contracts on a register machine at the end of the day, right? So what we have to, like, what the compiler or the interpreter has to deal is with the register allocation, and we don't want to do this on chain, right? Like like a single contract can have many contracts in the call stack, and and imagine compiling every contract in the stack, which can be a problematic, right? Like, you would have higher compilation times, and a lot of those contracts that are in the stack, right, they don't do a lot of work most of the times. And by the time this WebAssembly contracts have finished compiling, and we start executing these contracts, the Ethereum virtual machine would have executed the same contract like dozens of times. So I mean, it's a bitter thing to say, but WebAssembly loses hard in the average contract case. uh, is is like, anyone having questions? Are there any questions in the chat in this point of time? Hello. Hello.
Currently, we do not have any questions. So you can proceed further. Yes.
I'm audible, right?
Loud and clear.
Yeah. So then, so when we spoke about like, wasm contracts, right, we concluded that maybe wasm contracts are wasm contracts are not that good. Like, they lose hard in this average contract case, and it has high compilation issues. Then why did we not go with EVM contracts, right? And and to be honest, like, EVM is also not a very fast and a general purpose virtual machine, right? And it means the contracts that we write, those two are written in this domain specific language, which sometimes can limit what we can do with the contracts. And but with Polkadot, right, we want to innovate and remove the kind of limitations we have in this space. And this is something that, after looking at WASM and EVM, this is something that give rise to PolkaVM, correct? So what is PolkaVM, right? So PolkaVM is a RISC-V based general purpose machine, right? And it means like how we were limited to writing contracts in a single language, we can write contracts in a whole lot of other languages. And RISC-V, unlike WASM, is a register machine, right? The instruction set of this RISC-V, uh, the instruction set of PolkaVM looks a lot like the RISC-V with some minor modifications to make it on-chain friendly for us. And this PolkaVM supports this, as I said, this RISC-V instruction set architecture. So what you do is basically you compile your programs to the CPU, and when I say CPU, I mean this RISC-V, and then there is a linker which translates it into the PolkaVM block, which is what our palette revive can execute. So RISC-V is also, you can think of it as like very close to x8, like it's very close to x86 byte code. If you, I think in x86 byte code there are like uh, 16 instructions or something, and RISC-V has a more, but with minor modifications, we bring those instructions to match with those of x86. And all the compilation problems, right? Like as I mentioned, there is this stack in WebAssembly, right? And you have to map map the variables in the stack to appropriate registers. So but in, like, what if you use a register machine as register machine as a virtual machine itself? So your register machine has this uh, so your register virtual machine has this registers, and your actual computer has this architecture which is also has register, right? So this mapping from mapping from register to register machine becomes a bit easier compared to the mapping from your stack based machine to a register machine, right? So this is what we are doing with PolkaVM. This so this what this means is, unlike WASM, we can compile our programs much faster, and the compiler frameworks, for example LLVM, can spend a lot of time off chain producing very optimized blobs, correct? In our case it's the PolkaVM blob. So which means we have like a very efficient compilation, and the contracts we execute are very optimized and very fast. We also have gas metering in PolkaVM, uh, with gas models suitable for our contracts, which obviously, like, not all the WebAssembly implementations have. So there are two things. There is like this interpreter and just-in-time compiler. So interpreter basically means that we can start our execution instantly, just like how the EVM does, correct? uh, like if our contract is not doing a lot of work, interpreting is something which will be useful and faster than compilation. But in like compilation, we have to pay. In the case of PolkaVM, we just have to pay a fixed overhead of compiling. But once we are kind of done with this compiling, a contract can execute much faster, as fast as we can get fast as native performance. So there is this uh, there is this graph that I want to show. It's basically an iterations versus execution times. Like, what this graph is basically saying is that whether you want to use an interpreter, like PVM, basically in our case a prevm interpreter or a compiler, is a kind of an optimization problem, right? Like, when I say about iterations, like, think of like calculating a Fibonacci or a hash, right? Like if you have much iterations, correct? If you do not have much iterations, you would want to use something like an interpreter, like a PolkaVM interpreter, increase down the line. And if you look at the graph, if your iterations increase, you might reach a point where you would find that using an using a com, using a compiler is kind of better than using an interpreter, because it would give you less execution times, correct? And if you kind of look at the before this lecture, there was the slides about comparison between PolkaVM Solan, uh, PolkaVM interpreter, PolkaVM compiler, not the Solana RBPF, the WASM interpreter, which is the WebAssembly contracts that we use, and the WASM time, correct? Which this is what the WASM time is basically what the parachain validation function uses. So if you look at it, we have uh, we have better execution times than a lot of these other VMs. Like uh, if you speak about the execution time and you speak about the how long it takes to interpret. These are we have a better benchmarks on that. So what happens is like there is this whole lot of unlock contract use cases that we can tackle. So think of like instead of writing a parachain, you can kind of write your contract as a code. And in future, because like currently there is only this Polka VM interpreter, there is nothing called there is no compiler, right? It is in the just in time compiler is just in the works. But when this just in time compiler comes, right, you can, instead of maybe writing your parachain, you can write your code as a contract, correct? Because you will get the same performance as you get with the WebAssembly. uh, this is only feasible if you there is only if your startup overhead is feasible for you in the case of this, because the compilation might take time, but once it compiled, you would get near native performance. And and some of the other cryptographic use cases, you can build your own interpreter contracts for supporting other languages, or you can have this cryptographic algorithms that might be too expensive without these pre-compiles. So let's talk about this revive Solidity compiler. So now uh, we want to support EVM, right? But we want to support existing toolings, the libraries, the wallets, and everything, right? But the thing is, what we deploy isn't an EVM bytecode, correct? So so our solution, like what we do is we compile a Solidity code down to PolkaVM, plus the kind of Ethereum compatibility we get from our palette. So the end result of compiling to solid Polka VM and getting this Ethereum compatibility is we have something from the outside that looks like it would be an EVM, but actually isn't an EVM, correct? And the cost of doing this is having a decreased compatibility. But this kind of works for us because we are not actually an Ethereum. Polkadot is not like an Ethereum scaling solution, correct? So so the compiler we use, so our compiler, the Revive Solidity compiler, it uses the Solidity compiler as the Solidity front end, and then it asks the Solidity compiler to compile these Solidity contracts to YUL. And what is YUL? YUL is this intermediate representation which the SolC compiler internally uses, and it is and why this is good, because we don't have to write the Solidity front end, because writing it is kind of difficult, and there are many you know uh, there are many annoying things that happen. So what we do is we translate this YUL to an LLVM, and then ask the LLVM to optimize it and get us that Polka VM block. So this is about like so remember, like we are there is this in we don't go from uh, our contract to an EVM bytecode, but we go from like our soul C to this intermediate representation, and then this uh, like there are two intermediate representation. There is one YUL intermediate representation, then there is this ELF intermediate representation, and then the linker gives us the Polka VM blob. So there is this series of steps that we take to reach to our Polka VM blob. So this is one of the differences uh, differences between the EVM and the PVM. and and that is what I wanted to explain. Like, do we have any questions? Hello.
No,
Can you hear
currently
me?
we don't have any questions. So far, we don't have any questions. Should we open up for the
Hello.
questions? Because most of the people might be waiting for the Q&A at the
Hello.
end, right?
Can you hear me, guys?
Yes, we can hear you. We can hear you, Raj.
Hello.
We can hear you. Hello. Okay. Meanwhile, Abhiraj, do you want to go take over and go through the next segment?
Yeah, so most of it was covered by Raj. I have a couple of points to add to it. So as Raj mentioned that PolkaVM uh, is a separate virtual machine, and the Solidity code is compiled or interpreted into the risk instruction set, which is then run on the PolkaVM. So in between in these uh, interpretations and compilations, what we have is the YUL. So basically, when the uh, code comes in the YUL interpreter the intermediate step, the YUL uses actually a 256-bit word length. So that makes it a bit slow. But EVM, what happens in EVM is EVM uses the 256-bit word length throughout its interpretation. And when the code is transferred from Mule to PolkaVM actually converts it into a 64-bit word length, making the calculations and all a bit faster. So there is one advantage of using PolkaVM over EVM. And another insight is that you people might have noticed that we have to use a different remix than the normal one, right? So the reason behind that is that uh, the Revive palette is made using the LLVM based Revive compiler. So LLVM is nothing but the low level virtual machine. It's written in C++, and it helps the Revive palette to convert the Yule code, which is another intermediate language, the Yule code to the RISC-V architecture. So this LLVM is very compute heavy, and it needs a separate backend and separate logic, which is different than your normal EVM chains. That's why the Polkadot has made a separate remix for uh, deploying Solidity smart contracts. Yeah.
Perfect. Okay. So we actually showcase a little bit about the remix port, which is currently utilized for the Polkadot specific AssetHub chains. So currently we have Westend AssetHub testnet, then Paseo AssetHub testnet. Pretty soon we'll have it on Kusama AssetHub, and later on in the Polkadot AssetHub. So for all these chains, and potentially if we see other chains looking to adopt the palette revive, they can also potentially use this same remix fork, which is currently hosted, I guess, at remix.polkadot.io. And if you are looking for other resources corresponding to that, you can also check out the differences that you might need to um, do or understand, whether your contract is ready to deploy, and if you want to transition from like a standard EVM contract to the PolkaVM compatible, In that case, you will have to go through this documentation, which is currently hosted at contracts.polkadot.io. So this is where you will get all the resources, more about Riva compiler as well, installation, usage, architecture, the UL related specifications, which Abhiraj just covered. All these things you can find over here. But I guess for most of the contracts, you won't face any difficulties. But if your contract is complicated enough, you might have to review this document in order to not face any issues while compiling and deploying through the Polkadot remix.
Yeah, I'd like to add that we'll have a detailed session of deploying and writing a smart contract on, I think, 4th of June.
Mhm.
So we'll cover that things over there.
Perfect, perfect. Okay, so the demo part that we discussed at the start is scheduled for the 4th of June. And along the side, we'll have the AMA as well. But for now, if anyone have any questions, feel free to ask. We'll be now opening up for the questions from the hackers. Okay, Raj is here, so we'll add him real quick. Okay, so um, all the hackers who are listening us on the X live stream or the YouTube live stream, if you have any questions, this is a time to ask. So far, we haven't got any questions, but we actually have time specifically dedicated for this segment where we can actually even solve some issues, bugs, and specifically talking about the bug debugging. So we might be having active hours, active office hours on the Discord on a daily basis. So we'll announce that pretty soon, and you can join those office hours and get your bugs resolved in order to have your MVP ready in time. Okay, cool. Anything you would like to add, Raj, Abhiraj?
No, I think that covers it all. Yeah.
Sorry, guys, can you hear me?
Yeah, loud and clear. You are audible, Raj.
So we're starting with the demo, right? If we don't have any questions, I think Abhiraj was going to show some contracts, deploying contracts.
The demo part is scheduled on, we'll do it on 4th of June. The code, live coding and deployment.
Okay.
Yeah.
Sorry, I had some connection issues.
Mm-hmm.
Yeah.
Perfect then. Looks like we don't have any questions.
Yeah.
So we wish all the hackers who are currently hacking for getting to the top 12 to 15 places who will make it to the finale. Again, keep building, keep the spirit high, and if you face any difficulties, feel free to reach out us on the hackathon Discord or on the Students Collective.
Yeah. Also,
So
we have a front end session tomorrow for those who are stuck at developing good front ends for dApps. You can
mhm,
get that one.
yeah. So that's for this first workshop of this series. We'll be having 3 more. So definitely look forward to those and happy building. See you.